our goal for between now and next Wednesday is that we're going to talk a little bit about curve sketching. And this is going to be very different from our previous material, but it will rely on our previous material because we are going to use derivatives in order to understand the shape of various functions. So rather than having a lot of derivative rules or anything like that, instead we are going to have a few powerful theorems that are going to allow us as tools to figure out what shape the graph of a function is in. So let me write out the full word here. That's my abbreviation. So we are going to have definitions, and my abbreviation for definition is DEFN. You've seen this from me before. I'm just reminding you of these things. And my abbreviation for theorems is theorem, THM. And we're going to use these theorems. And every day we're going to have one or two definitions or theorems. You can probably average 1 to maybe 3 per day. And this is going to change the way that you study for this material. Because in the previous ones, you had to learn various derivative rules, and maybe we had to derive them. Here we're going to have theorems that follow the same pattern every time. If blah, 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 then blah, blah, blah. And you're going to need to know the if part, which is the condition, and the then part, which is the conclusion. And there is one and only one way to be able to successfully use those theorems, and that is to actually know what the condition is and to actually know what the conclusion is. Because if you do not know the conditions, you'll misapply the theorem. And if you do not know what the conclusion is, you won't know what to say on the basis of your condition being met. So you have to know these word for word. Which means that they need to go into your notes, and they also need to be worked on a daily basis so that they go into long-term memory. Right? There's no good waiting until the night before to study for this material. You just will not be successful if you try to do that. You won't. Trust me. I've tried. Okay? So that's our basic setup here. Now, let's actually see what we're really talking about. Today, we're going to be talking about increasing and decreasing on an interval. Now, what I'm going to do for this time period, this week that we're studying this, is I'm going to present some definitions. Definitions don't have proofs. They're simply names that we call things. We're also going to have some theorems, but I'm not going to prove these theorems at this time. I will in January. But for now, I'm going to present these theorems as intuitively plausible. When I say it, you'll go, oh yeah, that makes a lot of sense. Probably. Okay? So there's not going to be a lot of proof during this time. Instead, we're simply going to learn the theorems and use the theorems, and that'll be nice. So, here we go. Let's talk about what it means to be increasing or decreasing on an interval. If this is the graph of some function f of x, then you can see that intuitively it looks like it is an increasing function. And what makes it increasing, to speak informally, is that every time I go to the right, I also go up. Okay. So with that picture in mind, let's try to capture that picture in mathematical language. I want to capture the idea of when I go right, I go up. That's right. When x increases, y increases. Good. So let's say it like this. First of all, we're going to have an informal definition. We're going to say that f of x is increasing. Sorry, I want to do this in black. I'm going to try to color code all of this so that it's pretty in your notes. F of x is increasing on the interval a to b if. Here is our informal definition. We go up when we go right. Now, when I say this is an informal definition, what I really mean is that this is a slogan that you can use to help you remember what the language means, but it is not official language that you are going to use on any test or quiz. It's going to be for you to be thinking as the meaning of what we're about to say here. Now we need to really capture it. What we're looking at is we have an A and a B here, and to say that I am going right means that I'm picking 2 points. So I need to give them names, so let's call them C and D. And I need to observe that F of D is above F of C. Well, we can do that with inequality signs. So this now becomes our formal definition. I really wanted to do this in red, not black. There we go. Here's our formal definition. We're going to say that f of x is increasing on a to b if for any c and d in a to b, when d is bigger than c, that's our way of saying d is to the right of c, then f of d is bigger than f of c. In other words, this inequality is literally saying in math, when I go right, then I also go up. Does everybody see how the language means that? Well, it's not going to be too much of a surprise that we're going to define decreasing in a similar way. Informally, we're going to say that f of x is decreasing on the interval a to b if we go which way? If we go down, and we go to the right. That's right. We go down and we go right. And if you translate that into formal language, try again. We're going to have here an interval a to b, and we're going to pick 2 points, and we're going to pick d to the right of c, and observe that when I go to the right, I go down. And so we say that formally, excuse me, is that f of x is decreasing on a to b if when d is bigger than c again, then f of d is now less than f of c. Now, this is the most detailed definition or theorem that we are going to have during this entire week. It's sort of the base level, and so it requires special language to describe here. So if you're sitting here thinking, I'm going to have to memorize a whole lot of stuff, Don't worry about that too much. Our other theorems are going to be much easier because we're going to build on top of this. But this is the thing to know. This is the language to know right here.
So do you want to include a CGR part of IUD?
Yes, you're right. So I failed to mention that condition. Technically, B and C could be anywhere, right? And so I need to specify where they are. They are any points in the interval A to B. Is less than X. Now, in my other class, Bev Kimball asked a really good question, which was, shouldn't both of these be reversed? But actually, no. What we're saying is, if we go right, in other words, if B is bigger than C, then we go down. What happens if I reverse both of those inequalities? That would be saying, if I go to the left, then I go down. Is my function increasing or decreasing then? It's increasing, that's right. If I go to the left and go down, my function is an increasing function. If I go to the left and go up, my function is a decreasing function. Good. So flipping both of these signs would actually have the effect of saying exactly the same thing. Yes, sir. Well, no, there's another possibility actually, right? So if B is bigger than C, it could be that f of B equals f of C. And there's, right, that would be a constant function. And there's even a fourth possibility, which is yuckier than that, and that is that it could be that for some C and D, if D is bigger than C, then f of B is bigger than f of C, and for other B's and C's, it would be the other. So in other words, it may be the case that on an interval A to B, you might be neither increasing nor decreasing if you go up sometimes and down some other times. So it is not always the case that functions are always increasing or decreasing on a given level. Great questions. Okay, now we have this definition, but this definition strikes us as not being very, very usable to us. Imagine if I asked you, is f of x equals x cubed an increasing function on negative 1 to 1? Okay, that's a fair question. If you look at the graph of f of x equals x cubed, and it kind of looks like it might be increasing, but I'm not really sure about what happens right here at 0 because it kind of gets flat too. It's really hard for me to tell. So I actually need some tools in order to determine if a function is increasing or decreasing. Appealing to the definition would be hard because I would have to check every pair of B and C in the interval negative 1 to 1. And that seems a little bit challenging. I might be able to pull it off. In fact, I can pull it off for x cubed, but it requires some spiffy algebra. So instead, we are going to have a theorem, and this is our big theorem for today. It is the sine of f prime theorem. So this definitely wants to go into your notes because this is your very first theorem that we are going to be using here. And the sine of f prime theorem simply states that if f prime is positive on the entire interval a to b, then f of x is increasing on a to b. In other words, I don't have to go checking pairs. I can simply check the sine of f prime. And if I find that the sine of f prime is positive for every value in a to b, then I'm guaranteed that f must increase. Now, I'm going to leave this as an intuitive theorem. It seems kind of obvious. If I have a positive rate of change, I have to be going up. Does that make sense to everybody? I'm not going to prove it now. I will prove it in January when we have some extra tools available to us. I forgot to put my word then. All of our theorems come in the if-then form. So here is the condition. And that condition is going to become our justifying language. I guess the arrow is redundant if I have the then in place. And the conclusion is this part right here. So the way this operates is I'm going to check the condition, and if the condition holds, then I can draw the conclusion. Well, fortunately, it has a second part, and that is that if f prime is negative on A to B, then f is decreasing. On the interval A to B. This is at the heart of everything that we're going to be doing for the rest of our class period today. This is the center of it all. So we want to make sure that we have this language ready to go. Is it all in your notes and ready to go? Got it in your notes? Okay. Now let's actually see how this tool is very useful for us. I want to consider this function. Let f of x equal x cubed minus 3x plus 1. And I'm going to ask a simple question. What does the graph look like? Now, you might have some idea of what the graph should look like because you might recognize the family of functions that we're talking about here. Okay. So that's cool. But let's say you don't. Through the magic of calculus and the first derivative, and specifically the sine of f prime theorem, we can get a pretty darn accurate graph just by looking at the sine of f prime. And the way it's going to work is like this. We're going to consider the places where f prime is positive, the intervals for which is positive, and the intervals for which is negative. And to find those, we're going to find where f prime is equal to 0. And the reason we want to find the places where f prime is equal to 0 is that f prime cannot change signs without either going through 0 or failing to exist. You can't switch from positive to negative unless you either have a discontinuity or unless you go through 0. So if I set f prime of x equal to 0, and you're thinking, man, that's horizontal tangent lines. Yes, exactly. Then I can solve for the places where f prime is equal to 0. And these places we're going to call the critical points of f. Yes?
How do we check if there's jump or discontinuity?
If there's a discontinuity. Well, fortunately for a polynomial, I don't have to worry about that. For functions in general, there are some signs that you look for. For example, zeros in the denominator. That's the biggest way in which you can have an f prime is equal to, it fails to exist. So f prime is equal to 0. This gives me these 2 points. And now I'm going to construct for myself a familiar friend, the well-labeled number line. And I'm going to mark those 2 zeros for f prime right there. And these 2 zeros divide up the entire real line into 3 regions. And each of these regions is going to have a single sign, either positive or negative, according to whether or not the derivative is positive or negative. And it can't be both in a given region because you can't change signs without going through 0 or failing to exist. So that means that I can find the sign of this region simply by picking a number that is in this region and plugging it into f prime. Either plugging it in here or here, whichever is easier. Give me a number in this region, tell me.
Next year, one.
Okay, that is certainly a number in this region. Do you want to plug it into this one or this one? The bottom one? Okay, I like that. If I plug in negative 1.001, what do I get? Positive or negative? Positive. Okay, good. I probably would have chosen negative 2. Negative 1.0001, perfectly fine. Okay. Clara, choose for me a number in this interval. 0. Plug it into your choice of f prime. Negative 3, yep. And therefore, because that is negative, the entire region must be negative. And Mark.
2.
2.
It's positive.
It's positive. That's right. Do these regions always alternate in sign? No. Newbie mistake alert. You cannot just find the sign of one of them and then go alternating. For polynomials, it is the case that you can look at the degree of the factor here. And if your factor has an even degree, then it cannot change signs on either side, because whether I subtract a number close to 1 and get a negative, or add, subtract 1 from a number close to 1 and get a negative, or subtract 1 from a number close to 1 and get a positive, if I raise that to an even power, it will still be a positive value and I will not change signs. But if I have an odd power, it will change signs on either side of it. That works for polynomials. For other functions, you have to check each interval. So, just write a warning sign here. In general, must check each interval. Unless you're lucky enough to be dealing with a polynomial and you can check the degrees of the roots. Okay. Now, this work that we did here was not so bad, and you can imagine that with a little bit of practice, you can probably do this in under 30 seconds. Maybe a minute, something like that. Now, let me show you how we take that and convert that into a pretty good graph. I need a starting point, and a convenient starting point could be something like f of 0. What is f of 0? 1. And so that gives me an intercept for my graph of 0.0, 1. I'm going to indicate my critical points right here. And now I'm going to make my graph be increasing up to 1, negative 1, excuse me. Then decreasing, so I get to 1, and then increasing again after 1. See how easy that is? How well did we do? Let's find out. If I take my calculator here, and I let y equal x cubed minus 3x plus 1, double check that that was my function. Yep. Then graph it. Look at that. Look at that. My graph is pretty good. It's not perfect. I didn't go down far enough on this minimum value right here. And so I wonder, how do I know how far to go down? We'll cover that on another time. But as a general sketch of the shape, look at what we were able to accomplish with a little simple calculus. Isn't that nice? Newton loved this. In fact, Newton really was continuing on the work of Fermat who did this. Fermat called what we call critical points of f of x. Fermat called them stationary points because the derivative was 0. It was like the curve wasn't moving at that point. How are we doing so far? Does this make sense to everybody? Now, if we wanted to describe what's happening here, then we would describe the increasing or decreasing with the following language. We would say that f of x is increasing on the intervals -1, negative infinity to -1, union 1 to infinity. And here, we're going to say the magic language that comes straight from our theorem, because f prime is greater than 0. That's it. This language that follows the word because, that's my abbreviation here, because, we call this justifying language. It gives a reason that we are able to say increasing, and that reason can't be because I know what the graph should look like. The reason has to be based in a theorem, and the particular theorem that we appealed to was the sine of f prime theorem, and look, we copied that exact language. Because f prime is greater than 0, that let us draw the conclusion that f is increasing. Does everybody see how the logic of that language works? Okay. Let's do the same thing for decreasing. On what intervals is f of x decreasing? Mm-hmm. And our justifying language? That's exactly right. And tonight for your homework problems, every time you're asked to find intervals for which f is increasing or decreasing, you're going to use that justifying language that comes straight from our theorem. Now, in the time that remains, looks like you guys are doing well with this, I want to consider a problem that requires the use of a graphing calculator. And the problem, it's funny, because if I can use the graphing calculator, why don't I just graph the function? I get that question. What I'm doing really is setting us up for future work here, so play along with me. What we're going to do is we're going to pretend that our graphing calculator is selectively broken, so it can graph f prime but not f. We're going to pretend that. We know it's not really true. So we're going to consider a function that we started to work in the other class but ran out of time for, and that is, we're going to consider the function f of x equals x ln x. No, I'm sorry, it wasn't that. It was ln x over x minus 1. I think it was just x minus 1. Yep, it was just x minus 1. So we have now left the realm of functions that we know the families of. The last one, you maybe were able to figure out what the shape should be. This one, you probably have no idea. I certainly have no idea just looking at the equation. I am alert, however, to the fact that there may be a domain problem, because I have a denominator, and also because I know about natural log that it has a restricted domain. What is the domain of natural log of x? I can only take the log of what types of numbers? Positive, that's right. That was one of our 5 facts about natural log that you need to know, the domain and range. And so the domain of my function is going to be x is greater than 0, but wait a second. There is another value that I cannot use for x, 1. So I have to restrict my domain so that I'm talking about x's that are greater than 0 and x's that are not equal to 1. And now the question is, what does the graph look like? And again, I ask you to play along, because the easiest way to answer that question would just be to let y equal ln x over x minus 1 and find out. But we're going to use our calculus tools, and I'm setting up a situation in which we'll have to use the calculator to solve. Okay? We're going to use the same method that we did before. We're going to find intervals for which f is increasing or decreasing. And to do that, we need f prime. And so we do our usual. Low d high, less high d low, all over denominator squared. Do I simplify or not? Here, I do, because I need to use that derivative for something. So I'm going to simplify that to 1 minus 1 over x minus ln x, all of that over x minus 1 squared. now I'm ready to find the critical points for f. And the critical points are the places where f prime is equal to 0 or where f prime does not exist. Well, where are those points? F prime is equal to 0 when the numerator of my fraction is equal to 0. Fractions can only be 0 if their numerator is 0. And so I set the numerator equal to 0. And fractions will fail to exist when their denominators are equal to 0. Kind of remind you of the horizontal and vertical tangent questions that we had, right? Now the bottom equation is easy. I get one solution. I get x equals 1. And that x equals 1 is outside of my domain. So I'm going to handle that when I come to it by putting on my well-labeled number line at x equals 1, I'm going to put a circle with an x through it. And it is entirely possible that f prime could change signs on either side of that. But what about that top equation? That top equation is kind of funky. And it turns out that it is impossible for us to solve it algebraically for a really simple reason. This top equation contains a mixture of exponentials, really logarithmic functions, and also algebraic functions. There's no way to get those equal to each other. So because I cannot solve this equation algebraically, I'm going to solve it on a calculator instead. And I do that exactly the same way that we've solved all equations on a calculator. I'm going to let y1 equal the left-hand side, y2 equal the right-hand side, and do second calc intersects, or in this case, second calc 0. So we go to our calculator here, and we let y1 equal that right-hand side, 1 minus 1 over x minus the natural log of x. Like so. And then we let y, we're going to just find the zeros, right? So then we graph this guy. And when we graph this guy, it looks like there might be a 0 right here. So let's actually zoom in a little bit and see if we can find a 0. We're going to change our window size so that the y values are amplified, more clear. We'll make that y go from -2 to 2. And now when I graph it, ooh, it does look like there might very well be a 0 right here. And that point looks like the point x equals 1. Let's trace around and find out a little bit. And when I trace around to x equals 1, I get y equals 0. That's an interesting thing, because I observe that when x equals 1, technically I'm outside of the domain of my derivative. So what does that mean for us? Well, what that means for us is that my numerator does in fact equal 0 at x equals 1, but my domain trumps that fact. I'm going to have a domain that does not include 1. Okay? With that in mind, we're going to say that the only solution is x equals 1, which is excluded. Now let's come back and construct our well-labeled number line. First, we need to put a boundary on our domain. We cannot include any values, make that an open boundary, any values of x that are less than or equal to 0. Second of all, we have these two intervals that are defined by the one critical point, the point where x is equal to 1. So I have these two intervals that are defined by the single critical point x equals 1, and the bonus part of my graph is that it immediately shows whether my derivative is positive or negative here. Well, no, it actually shows the sign of just the numerator. So let's go back to our equation and plug in a value of x that is greater than 1, plug in a value of x that is less than 1. If I plug in a value of x that is less than 1, let's say 1/2, then what I get is 1 minus 1 over 1/2, which is 2, minus the ln of 1/2, divided by 1/2 minus 1 squared. And when you work all of that out, then it turns out that that value is less than 0. Your calculator can tell you that. Likewise, if I try something like x equals 2, then I get 1 minus 1 over 2 minus ln 2, all over 2 minus 1 squared. That turns out to be less than 0 as well. So I get two different intervals for which my function is decreasing. So this is a really good example of a function that does not change signs on either side of the critical point. So I'm now ready to put this whole thing together. To sketch a graph, what I've determined is that my function f is decreasing on both of those intervals here, and I'm going to state that. It's decreasing on the interval 0 to 1 together with 1 to infinity, and now comes the magic justifying language, because a prime is less than 0. For my graph, I'm going to represent the fact that my denominator goes to 0 right here. Well, that's clearly a point of discontinuity. Is that point of discontinuity going to be an asymptote, or is it going to be a hole? And to evaluate that, I need to take the limit here, like so. That limit turns out to actually be kind of challenging. Kind of goes beyond the scope of our course. But if I were to take a number that is close, excuse me, second, quick, a number that is close to 1, such as 0.9999, and compute the natural log of 0.9999 over 0.9999 minus 1 to estimate the value of the limit, then I get something that's very close to 1. And so because I get the value for that limit, appears to be 1, that leads me to conclude that I have a hole in my graph. So I need a function that is going to be decreasing, that has a hole in the graph at the point 1, 1, and decreasing on both sides. And so my graph is going to look something like this. Whether it has an asymptote or not is going to be hard for me to determine without some additional tools. We compare this to the actual graph of the function of ln x over x minus 1, then we can see that with our calculus tools here, we did a pretty good job with our graph. Notice that our graph does indeed have a hole at x equals 1. If I trace to x equals 1, then we have no y value right there. Well, I hope this was helpful to you as an example of an advanced type of analysis with derivatives. The first example with the cubic would be a more simple example. We're going to continue with this tomorrow, and tomorrow we're going to pick up on the question of how do I know how far up or how far down to go. Talk to you later.